John Renner, who is talking about CT-Wasm. I don't know if I'm pronouncing that correctly. Type-driven secure cryptography for the web ecosystem.
You're coming with me. And full screen that. Sweet. You good to go? Awesome. Hey, everyone. First off, I would just like to thank all of the collaborators and other people who helped this whole thing happen. So today I'm going to tell you a bit about CT-Wasm, which is an extension to WebAssembly that provides secure cryptography for the web. But before we really get into to what it is and how it works, we should understand why we need it. And we need it because writing crypto code is hard. And it's hard because it's not the same as writing regular code. Functional correctness is not enough for us. Let's consider this encryption routine, where we try to encrypt a message with private key 1, and it takes 25 nanoseconds to complete in the real world. And then we attempt to encrypt the same message with private key 2, and it takes 20 nanoseconds to complete. This means an outside observer can distinguish between the two inputs purely based on this timing information. And this vulnerability can be exploited to actually steal the private key, impersonate you, do all the terrible things you can do once you have one. This is bad news. And while, yes, it seems like, yes, you could do this, maybe, but it's kind of too academic. Thankfully, there's plenty of academic research telling us how it's not an academic problem. We have the papers, remote timing attacks are practical. Remote timing attacks are still practical. Hey, you, get off my cloud, and others. All of these typically target trying to steal OpenSSL certificates, and they do it with great success, real vulnerabilities that they were able to exploit. And these vulnerabilities have been addressed with carefully crafted C code that we compile on low optimization. And if we're very careful, we can make our implicit timing properties safe. But here's the problem. People aren't just writing crypto in C. They're writing it in JavaScript. And to illustrate why this is a problem, I present this meat grinder. But for our purposes, we're going to call it a JavaScript runtime. And the meat grinder takes your JavaScript code and outputs fast machine code. That's what it does. You give it scripts, it gives fast machine code. But in doing so, it's going to rip apart your program. It's going to insert things, remove things, restructure things in order to get the fastest result it can. The problem is, just like a meat grinder, it does one thing with whatever you put in it. So if we put in constant time code, it will give us fast code, but not guaranteed constant time code out the other end. Unfortunately, JavaScript cryptography is more popular than ever. Signal, the secure messaging application, uses the JavaScript crypto library for their desktop application, which is written in Electron. And Google's crypto library has over 400,000 downloads on NPM per week. So there's a lot of this code running around. But we can't entirely just fault the developers and say, oh, well, you just shouldn't have written it in JavaScript. They don't have a lot of great choices. There are some. They could use the platform-provided crypto primitives, which are web crypto on the front end and Node.js crypto on the back end. Note that they're different, and you can't share your code across them. And not only are they different, they're missing key modern crypto algorithms. And so if you want that algorithm, you have to ship your own code. On Node, we can do this with C modules that we link against. But again, this won't work on the client side. And developers often just opt for the library that works everywhere. Or if they're on the client side, they're kind of trapped. So if we want to solve this problem, we have to provide them with a solution that meets their needs of portable cryptography. So we could extend JavaScript. We could say, OK, let's carve out a section of JavaScript and find a way to make it safe for constant time. But there's a lot going on in this language that makes this difficult. It has complex dynamic semantics. The JIT is going to cause all sorts of crazy deopts and optimizations to happen. And the garbage collection likely leaks. We're looking into that some more, but yes. Thankfully, it's not our only option. In 2018, every major JavaScript runtime shipped WebAssembly, which is a new language that can also be run on the runtime, that is statically typed, low-level, and still portable. These statically typed programs will help us increase our guarantees. And being low-level means that we're closer to what our crypto operations are really doing. So maybe this helps. It looks sort of like this, because you're going to see some code today. WebAssembly is organized into modules that contain functions. This function adds 2 integers. It's a stack machine, so we push both integers onto the stack, perform our add and return. Nice and simple. And then, because this is built to work alongside JavaScript, we can export these functions so that JavaScript can call them, in this case, under the name addInts. But this still isn't enough. We have no guarantees that our code is constant time. We could structure it properly, and we could try. And even if we do manage without these guarantees, the runtime can still introduce vulnerabilities. This code still has to be translated to machine code at some point. So we have no guarantees, but things are a little better. So we're going to take WebAssembly, and we're going to add stuff to it. We're going to do this by to make secrecy explicit. And we'll do this by adding 2 types. These represent secret integers. So S32 and S64 are 32 and 64-bit secret integers. The other 4 types in WebAssembly we will consider public. So all code written today operates on public data. And we're going to use these types to turn these vulnerabilities that we're worried about into type errors. And then we're going to, once we've type checked, we can use these types to inform the runtime during compilation to not ruin the properties that we've so carefully built. We're going to prevent 3 kinds of vulnerabilities. First, explicit leaks, which is we'll get into. So for example, consider we have a public and a secret integer, and we want to store the secret integer into the public integer. This is obviously bad. We should not do this. Thankfully, now that they're different types, it's just a simple type error. It's nothing special. But this doesn't actually protect us against all direct leakage. WebAssembly has a memory, and so it doesn't have a heap, but it has a dynamically sized linear memory in which you can store things like an array. So if we store a secret into here, the memory is untyped, so we can read any type out of it that we want, which will allow us to just load that value back out as public. And again, we've lost track of the fact that it was secret. This is bad, and we don't want to allow this. And we could solve this problem by trying to keep track of places in memory that are secret and some that are public, and there is like a lot of literature on this. But we need to be really fast because we have to validate in the time it takes a page to load. So instead, we introduce a new memory. You can just say, this memory is secret, and it only gets secrets in, and it only gives secrets back out. And so now we have 2 disjoint memories. You can have secret memories and public memories, and never the 2 shall meet, which is great. And that keeps us from like the obvious leakages. Things that are secret stay secret. But there's some more surreptitious ways that we could leak. Consider this program where we say, if some secret condition, we are going to write into a public. So now the value of that public depends on the secret's value, which is obviously bad. We've leaked derived data. There's actually 2 leaks going on. One is that we're actually flowing from the public from the secret value into the public value. There's also a timing leak here, which is that branching on secrets is generally considered not constant time, in that it could take a various amount of time to execute. So we want to completely disallow this. And we're going to say, you cannot branch on secrets. And while this may seem draconian, it actually is totally fine for implementing crypto, which we'll demonstrate with our algorithm implementations later. Sweet. Now we can finally get down to more of our timing problems. At the base level, certain instructions are constant time and certain ones are not. So if you're doing integer division on a modern x86 or ARM processor, it's most likely not constant time. Depending on your operands, it will take a different amount of time to execute. So we're just not going to allow this, because otherwise you could tell what operation you were performing. Thankfully, most operators in WebAssembly on integers are entirely constant time, so add, XOR, sub, multiply. The only 2 we have to disallow are division and remainder. Unfortunately, floating points, on the other hand, are notoriously almost entirely variable time. So they're going to leak no matter what we do, which is why we have no secure floating point type. It turns out, again, serious crypto algorithms don't use these, so today at least, so it's fine. There's another kind of timing attack that can get us, which is the cache. Consider we're loading a value out of memory based on a secret value. So we say load at some secret index. It could be 4, it could be 7. The problem is, depending on where we load from, that's going to affect the cache state. The cache will enter in, get new lines, and then what happens is every memory operation is going to both mutate the cache state and leak its state via timing, based on whether it's quick or slow. So this means that our cache state needs to be independent of secrets. Otherwise, we'll be leaking them through this side channel. And so we completely disallow secrets as memory indices. What this does mean, it doesn't mean you can't store secrets, right? We have a memory for it. It just means you can't index into memory using these secrets. Unfortunately, we've constructed a language so far, if you've been paying attention, that's too safe to do anything real. Let's consider the case of encryption. Encryption fundamentally takes some data that is secret, you run a routine on it, and you produce a value that's public. It's safe to share with the world because it's no longer protected by policy, it's protected by math. Unfortunately, our type system doesn't let us do this. And, well, where have we gotten if we can't write helpful routines? So we have to introduce a new opcode. And this opcode is declassify. And it takes something that is secret and makes it public. And you may be thinking, well, what's the point? We went to all this effort to keep things secret, and now we're just making them public again. While this is necessary, it is entirely unsafe. And so we want to restrict the places in the language where we can actually use it. We do this by introducing the notion of an untrusted function. And this is a function whose implementation you don't trust. So you want to make sure it doesn't leak. These can no longer call declassify, and they can only call other untrusted functions. Thankfully, all of our crypto code that we implemented is untrusted, so it's not a problem. We can do the declassification on the last mile, just on the way out. This creates a world where once a trusted function calls into an untrusted function, we know that nothing's going to leak until it returns, which is a really strong property. So all of our proofs of safety and stuff are going to be modulo being inside one of these untrusted functions. This has a cool side effect, though. WebAssembly requires us to assert the types when we import something. And so if I import from a library an untrusted function, I don't even have to look at it to know that it's not going to leak my secrets, which is really cool. So because we explicitly import with the type checker will ensure that whatever this function does, it doesn't leak. And you can take my word for it, but instead we have proofs. We've verified the language in Isabelle, and there's several properties we prove in the paper, but we're going to highlight two in this presentation. The first is the property that prevents the explicit and implicit leaks that I talked about before. And there's a formal name for this. It's called non-interference. And the intuition is that a function's public outputs are independent from its secret inputs. So if we consider a computation as taking a set of public inputs and secret inputs and producing a set of public outputs and secret outputs, then if we shake up the secret inputs but keep the public inputs exactly the same and perform a computation, we should get the exact same public outputs. We have formalized this, we've proved it, we have it. But this is not enough to protect us from our side channels. All we're talking about now is bits. We're not talking about things that leaked via timing or other ways. So we need a stronger property, which we call the constant time property, and it's a well-known formal property. And we state it as a program's leakage is independent of its secret inputs. So now, rather than talking about output bytes, we're going to talk about program traces. And we're going to say for a given public set of public inputs and secret inputs, we get a program trace. If we shake up the secret inputs, we'll get a different program trace. And the trace is just a list of operators and operands. But because we disallowed branching on secrets, our control flow is entirely independent from secret values, which means that the sequence of operations is not changed by shaking up the secret inputs. All that changes is the secret operands. As you'll see here, this S32 add now has different operands. But that's OK, because if you'll recall, we picked explicitly operations that don't leak. There's much more in the paper about this formalization, but this is sort of the intuition of how it works. And this is all well and good. We have a very strong theoretical understanding of how this works. But can we build it into a real system and get the properties that we want? Well, we built it into two systems. The first system is the reference interpreter that's provided by the WebAssembly committee. It's written in OCaml, and it comes with a full suite of tests for how WebAssembly is supposed to work. We extend this test suite with our own behaviors, and we even extract the type checker from our proofs and provide verified type checking in OCaml, which is kind of fun. It's a step forward for both WebAssembly and CT-Wasm, as it was previously not verified. Similarly, we implemented it in V8. And this is important because the reference interpreter is not going to give us an indication of how this performs in the real world. It's not going to tell us, can we build applications and get the real world performance we need. So V8 is the runtime that backs Node.js and Chrome. And it's a large C++ project, which we have extended to support CT-Wasm. And this gives us an understanding of what a production quality runtime will do with this code. Unfortunately, because it's such a large C++ code base, we won't be able to verify it, but we will be able to empirically analyze the timing behavior. To evaluate our runtimes, we created several crypto implementations. the tiny encryption algorithm, SHA-256, which is a hashing algorithm, Salsa-20, which is a stream cipher, and TweetNackle, which is actually a reasonably large library of crypto algorithms that all work together with a higher level API. If you're familiar with Knackle, it's just a WebAssembly version of it. And these show that there's many different kinds of crypto algorithms that we're able to implement successfully, again, using untrusted functions. We do have a bit of an overhead that we found, though, which is that our binaries are a little larger. And they're larger because WebAssembly uses 1-byte opcodes, but there were not enough available opcodes to introduce all of our new ones. So our new opcodes are all prefixed with 1 byte, so it takes 2 bytes to encode each. And this may be really scary. You're like, double the binary size. People have to download this stuff. But it's actually only about 15% in practice. This is because much of the binary is devoted to control flow, which is public, interfaces, types, things like that. So in practice, our libraries are about 15% larger than their unannotated counterparts. And we have 0 binary size overhead for vanilla WASM code, which should be obvious. We are a direct extension, so all old code continues to work, and I didn't get any bigger. Oh, cool. As for performance, during runtime, we're less than 1% different, which could just be noise. We're doing great there. In type checking WASM, we have a 14% overhead, and we believe this to be just regular unannotated WASM. And we believe this to be because of the changes we had to make inside V8. We introduced a new operation that had to be performed during type checking that we believe could be removed with more engineering work, but I don't work for Google. In type checking CT-Wasm, we have about a 20% increase in time. And we account this largely to the binary size because the type checking algorithm is a linear pass over the bytes. And so by increasing the binary size, we increase the time it takes to type check. But still, don't let these big numbers scare you. We're still sub-millisecond for this library of like 8 crypto functions. So while this is a good percentage increase, absolutely in the real world, we're doing fine. But we still need to know if we actually ended up constant time at the end of the day. And so we use this existing tool called DudeCT. And DudeCT measures the statistical relationship between the inputs to a function and the time it takes to execute. And so, for example, we took the Salsa-20 package off of NPM, and it's implemented in JavaScript, and we ran the tool on it. As the tool takes measurements, its understanding of the correlation increases and says, wow, there's a pretty strong correlation. If you're above that dashed line, which is very close to the axis, you are not constant time. So we are wildly unsafe in this JavaScript world, which validates all of the concern we had at the start. But if we take our CT-Wasm implementation of TweetNackle and run this tool on it, we stay well below this line and are empirically constant time. Now, remember, this doesn't mean that every program we write in CT-Wasm compiled through V8 is going to end up constant time at the end of the day. We believe it will be, but we don't have a proof, and we'll talk more about that next. And this is great and all, but it requires the runtime to agree with us, which no one is running CT-Wasm if you're not at UCSD. So can I use it today? You can. We provide a tool called CT-Wasm, which takes your annotated code and spits out WebAssembly that can be run today. And it still gives you that type checking guarantee to ensure that your program is structured properly. And we actually do a best effort program transformation to protect you from the runtime. For example, in V8, the select instruction is variable time. It uses an actual if, a conditional jump under the hood. And so we actually restructure your program to do some bit magic to protect you from that. This code is today constant time as well on V8. But here's the problem. This is sort of a cat and mouse game that we play with the runtime that we don't want to, that you don't get all the guarantees. Looking forward, we have some goals of doing verified compilation, which I said we don't have. Regardless of whether this works or not, CT-Wasm is very interesting as an IR for high-level crypto languages on their way down to the machine. And we're also looking at label inference to allow existing libraries to compile today. With that, CT-Wasm exists today. It's a type system for secure crypto that is formally verified in Isabelle, performantly implemented in V8, and usable today through CT-Wasm. With that, I'd like to open up for questions.
Okay, let me just remind folks that you can ask questions on Slido if you want to. Any questions?
Yeah, can you say a bit more about your notion of constant time in your Isabelle formalization? So do you have an actual notion of time there? How does it work?
Yeah. So traditionally, constant time is modeled as a series of observations. And so we say over a program execution, if you leak the same observations, then you are constant time. We can talk more about this offline, but basically we don't model real-world time. We model observations.
Okay. In the interest of getting back on track, I think I'm going to ask that further questions be offline.
Cool.
So our next speaker is Caleb Stanford.